So in this module, we're going to talk about how we can apply those concepts of matrices and vectors that we introduced in the last module in order to solve systems of linear equations. So before we actually go into detail, we need to define what a system of linear equations is. So this is probably the simplest example of a system of linear equations that you've seen. And you might say, well, this doesn't look simple. There's a lot of letters there. What is A? What is B? And so on. But in this case, X and Y actually denote the unknowns. And in practical scenarios, A, B, C, D, K1 and K2 are actually going to be numbers. So if it helps you, just pause the video and write down and just pick some numbers for A, B, K1, and so on. Make A1, make B2. And what you'll see is if you set the equations up that way, each equation individually is nothing more than an equation of a line. And remember that an equation of a line has an infinite amount of solutions. Any point on that line, if you plug in the values of X and Y, satisfies the individual equation. However, this first equation will have an infinite amount of solutions. The second will have an infinite amount of solutions. But in most cases, if you graph two lines, they're only going to intersect at one point. And what's special about that point of intersection? That point of intersection is on both lines. And what that means is that it satisfies both equations. So that's what it means to be a solution to a system of equation. It's the value of variables that if you plug them into each equation in the system is satisfied. So how can kind of the matrix vector techniques that we spoke of in the last lecture help us with solving these? Well, all we're going to talk about for this first setup is how we can rewrite these systems of equations in what is known as matrix vector form. And that's exactly what I'm showing you here. So let's take a look at kind of what happened when we went from the system of equations to matrix vector form. We got a matrix, particularly it's 2 rows by 2 columns, or 2 by 2. We have a column vector, and these two things are kind of written next to each other, and usually in math that implies that they're being multiplied. So this matrix multiplied by the column vector is equal to another column vector. And let's actually go into more detail about each of these individual matrices and vectors. So this the first matrix that we have here, which is 2 by 2, if you notice the first row of the matrix, the elements in that row, A and B, are the coefficients of the variables in the first equation. So the coefficient of X is A in equation 1. The coefficient of Y is B in equation 1. So note that in row 1, we have an A in the first column and a B in the second column. In a similar fashion, if we look at row 2 of this matrix, we see the coefficients are the numbers that are multiplied by the variables again. Again, the number that is multiplied by X in equation 2 is C. There it is. The number that is multiplied by Y is D. There it is. So really what's happening here is we see that this matrix has a structure. Each row corresponds to an equation, and each column corresponds to a variable. So the first row corresponds to the coefficients of the first equation. Column 1 is the coefficient of X. Column 2 is the coefficient of B. And hopefully you see that pattern, but we're going to do an example here in a minute and show you kind of a case where there's not A's and B's and K1s, there's actual numbers. But not surprising that what we're going to call this 2 by 2 matrix is actually the coefficient matrix. And here we're denoting it by the capital letter A. This vector, this column vector, contains the two variables that we're attempting to solve for. So we're going to call that the unknown vector X. And when the coefficient matrix A is multiplied by the unknown vector X, we're going to get another vector, which we're going to call B, and that just has the constants of these two individual equations. So before we go on, we should have said something about the structure of these linear equations in two variables. If you think back to when you solved this originally in algebra, each of these equations is in a particular type of form, and that form is what is known as standard form. And in standard form, all of the variables in an equation are on one side and all the constants are on another. And what we try to do is align the terms involving common variables on top of one another. What I mean by that is, in addition, you can always swap the order that you write two things that are being added. However, we'll choose to write the x's first, and we could have just as easily chose to write the y's first. But if in equation 1, the x term is written first, then in equation 2, the x term will be written first as well. So that is known as standard form. So if you think about just one more thing, if you look at the format here, when we converted the system of equations into matrix vector form, we kind of see that there's a natural kind of meaning about what happens when you multiply a matrix times a vector. So in this case, we multiplied the coefficient matrix times a column vector, and we got another column vector. And we will say something about that in more detail when we go into the next learning module. So let's look at an actual example problem here. This is a little bit different because we have 1, 2, 3 equations. And in addition, there are 3 unknowns, or 3 variables. The first equation involves variables x and y. Second involves variables x, z, and y. And the third involves only z. So what we're trying to do here is to rewrite this into matrix vector form. And let's take a look at how that would actually work. So here are the individual equations that I was given, and I'll upload these solutions as well. That's why I chose to write them rather than to use a .cam. That way I could write a little bit cleaner. The first thing we want to do is to put each of these three equations into standard form. And standard form means all the variables on one side, all the constants on another. So I'm going to choose to move all my variables to the left side. In addition, I'm going to choose whenever a variable that's in one of the three equations is missing, I'm going to write it into the equation with a coefficient of 0, just to keep things organized. So let's look at equation 1. X minus 2y equals 3. That's already in standard form. So all that I could really do is just make my life a little bit easier by explicitly showing some coefficients. So what is the coefficient of x? Well, if we don't see a number there, we know that it's implied that it's multiplied by 1. What is the coefficient of z? Well, since there's no z term, I'm just going to add a plus 0z so that on the left side of the equation, I have my x term, my y term, and my z term. What about equation 2? Well, if you look at equation 2, it's not in standard form because the variables involving x and y and z rather are on the left, and the variable involving y is on the right. So the first thing that I want to do is transition that term involving y to the left side. If I have a plus 3y on the right, the way that I eliminate it is by subtracting 3y. In an equation, I can always subtract something from one side of the equation as long as I do it to the other as well. When I subtract 3y from the left side, that doesn't combine with anything. There's no like terms. I only have x's and z's. So the result is simply going to be 4x minus 3y plus 2z equals 0. And that's in standard form. And it's organized in the same order that equation 1 was. X term, y term, z term, x term, y term, z term. What about equation 3? We'll notice that it doesn't have an x or a y, so I'll just add in 0 coefficient terms for the x and the y. So 0x plus 0y plus 2z equals 4. So now that I have the three equations in an organized standard form, I need to put it into matrix vector form. And the way that I'm going to do that is since I have three equations and three unknowns, my coefficient matrix will be 3 rows by 3 columns, or 3 by 3. In row 1, I'm going to have all the coefficients of the variables from equation 1. Since I chose to order them with x's first, y's second, and z's third, I'll have the coefficient of x, which is 1, the coefficient of y, which is minus 2, and the coefficient of z, which is 0. I'll do that same thing for equation 2 here. Coefficient of x is 4, coefficient of y is minus 3, coefficient of z is 2. And you'll notice those are the numbers in the second row. For the third equation, the coefficients are 0, 0, 2. Notice in that third row, 0, 0, 2 are the elements of my coefficient matrix. What is that being multiplied by? Well, it's being multiplied by the unknown vector that has elements x, y, and z. And again, with the reason that we structure the x first, the y second, and the z third is that's the way that they're ordered in the coefficient matrix. First column was the x coefficients, second was the y, third was the z. That product of the coefficient matrix times the unknown vector is equal to a column vector that contains just all the constants of the individual equations on the right side. So since equation 1 had a 3 constant on the right, it goes first. Equation 2 had a 0 constant on the right, it goes second. Equation 3 had a 4 constant on the right, it goes fourth. So if you notice that matrix vector product, I just have some notes for you there to kind of make it easier and explain. But if you take off all those notes and just circle your final answer, you have a 3 by 3 coefficient matrix multiplied by the unknown column vector, and that product gives you the constant vector on the right. So hopefully this was helpful to you, probably a little bit of review, but that's always good. And I will see you all in the next video.